All right, it's 4 o'clock. Thank you everyone for joining. We will begin, we'll just give another minute or so to allow other people to join, and then we'll begin. All right, it's a minute or so past 4, so I guess this is a good time to begin. Again, thank you everyone for joining this VLE. In this session, we'll be trying to recreate the model that this DeepDTA model described in this paper that we sent out. And the objective of this paper was to build a model that could predict drug target affinity. And this model used two data sets, the Kiba data set and the Davis data set. And they're both data sets that contain information on binding between various drugs and various kinases. We will be attempting to reproduce this model using the Davis data set because it's a smaller data set. And that data set is described, or the production of that data set is described in this paper. And in this paper, the authors, they did many competition binding assays to determine the dissociation constant between a given drug and a given kinase. And obviously, the objective of this paper was to identify novel kinase inhibitors. This is obviously very important, mostly for cancer research, but also other diseases. And so one thing I should say about this paper is, obviously I got the data set from this paper, but the data set comes as this, as a matrix of drugs and kinases. And so it requires a little bit of pre-processing before it is in an appropriate form for analysis. And I've done that pre-processing. And as I'll mention at the end of this talk, I will ask Tiffany to send that data set out to everyone, all the people who've registered, along with the code. So I think the best way to participate in today's VLE is to just watch me go through my code. And please, if you have any questions, I'm here to answer them. And if you would like to reproduce this yourself, it's probably best if you do that while listening to a recording of this talk, and this talk will be recorded. Okay, so I'm going to do everything today in Google Colab, which is kind of like a Jupyter notebook. You can think of it as a Jupyter notebook that lives in the cloud. It's free to use. And importantly, it allows you free GPU access. I have a Colab Pro subscription that's really cheap, and it gives you kind of unlimited access to GPUs. So it's slightly better than the free version. So I guess we can begin. I have, as I mentioned, I prepared this data set or pre-processed this data set, and I've called it DTA_DF.CSV, and I've already uploaded it into Colab, so I can easily import it. Today we'll be using TensorFlow and Keras. To build our model, we could easily do this in PyTorch or any other popular deep learning framework, but TensorFlow and Keras especially offers this pain-free and easy way of building neural networks. We'll be using some other popular Python packages like Numpy, which is the workhorse of machine learning and deep learning, and a few other packages. So I'm just going to go ahead and run this. Oh, and I should say that if you want to enable GPU use, you just go to runtime, change runtime type, and then set your hardware accelerator to GPU. The default is none. So the default is just using a CPU. Okay, so that's loading the packages. And since this is deep learning, there's a lot of stochasticity. So to ensure repeatability, we need to set our seeds. And so I've set 3 seeds here. One is for NumPy, one is for TensorFlow itself, and the third is I'm using this random package, or I will use this random package, so it has its own seed. Okay, there are various ways to load our data. So I should say that the data that we will load, it has just 3 columns. One is the drug column. Now, the drugs, they come in the form of what are known as smile strings. So obviously, drugs are 3-dimensional objects. One way to represent them in a 1-dimensional form, which is what the DeepDTA authors do, is to convert the drug to this thing known as a SMILES string. And SMILES stands for Simplified Molecular Input Line Entry System. There's a nice Wikipedia article that describes how SMILES works. And I won't go into too much detail about that, but just to kind of quickly show you what a SMILES string looks like. There are some nice examples here of, like, for example, melatonin, which has this structure here. This is what the SMILES string looks like, and so on. So that's the SMILES string. I should close this. So we have a SMILES drug column, which has the drugs represented as SMILES strings. We then have a protein column, and the protein here, again, is represented as 1-dimensional data. In this case, it's just the amino acid sequence. And then we have, so I mentioned the dissociation constant. So this is the KD. That was what was worked out or quantified in the Davis paper, so this Nature paper. What the DeepDTA authors did, let me see if I can find it, is they found that by converting the KD values to PKD values, and there's a formula here for doing that transformation, that yielded better results. So as you will see, for most of the decisions about data transformation or hyperparameter choices, I just blindly went with the ones that DeepDTA recommended, just so that we could compare our results with theirs. All right, so that's it. So we have 3 columns: SMILES, sequence, and PKD in our data set. And I wrote this, here's a little for loop for creating a list of lists of the SMILES sequence in PKD data. And that list of lists is just this data object here. And if we look at the length of the data object, we see that there are 23,785 entries. I should say that since I was the one who did the pre-processing, I did notice that for a few drugs, for whatever reason, I couldn't get the corresponding SMILES string. So my pre-processed data set is slightly smaller than the DeepDTA one. And I think that's fine for educational purposes, but obviously if you want to use this for your own research, please double check what I've done. But yeah. And if we want to peer into this list of lists that we just created, this data object, we see, sorry, that's just a comment to myself that things look good. We see that there are 3 entries for the 0th entry. So we can see there's a SMILES string for that drug. Then there's the amino acid sequence for the given protein, and then the PKD value, not KD, but PKD. And then what I did was I wrote another for loop. Well, I first shuffled the data, and then I wrote another for loop to split the shuffled data into three different lists: a smiles list, a proteins list, and a labels list. And once again, just to see that everything looks fine, I printed the 0th entry for each, and you can see that you are getting a sensible output for each entry. Right. So we have our data in, and we've shuffled it, which is important. The next thing to do is to split our data into training set to a training set and a validation data set. So if we go through this code here, in this case, I've made the decision to split our data so that it's 90% training and 10% test. So I just work out what that is, what the split point is with this first line of code. And then I just divide split the lists into the training lists and the test lists. I do it for the smiles. So you can see I have a train smiles and test smiles. I do that for the proteins data, and then I do that for the labels data. So I'm calling the PKD here labels. So this is pretty straightforward. Okay, so far, especially if you've done any kind of machine learning or deep learning, all of this is kind of how you would set up your data to do the analysis. Now comes the part, the deep learning part, the model building part. So before I proceed, so in the paper, they do a thorough job of categorizing their data set. So they show you the distribution of PKD values, the distribution of smile strings, the lengths, and the distribution of the length of the protein sequences. And they do this not just as kind of exploratory data analysis, but they also do this to help them define important hyperparameters that we will go over in a few minutes. So this, I hope everyone can see this clearly. This is a depiction of their model. And you can see that in this case, we can think of this model as having two towers. One tower, which is its own neural network, corresponds to the smiles input, so the drug input. And the second tower corresponds to the protein sequence input. There have been many previous VLEs on convolutional neural networks, and that's what we will be using today. The one difference between the convolutional neural networks that you might have seen previously in this one is the previous talks have all been about how you can use convolutional neural networks to do image analysis. And we will see in today's talk that you can just as easily use convolutional neural networks to analyze text. And actually, everything that I'll be showing today is, you can think of it as a kind of natural language processing approach, except instead of sentences, where each sentence is made up of a word, we have these two different kinds of sequences: a smile strings, where each smile string is made up of an atom or a bond, and our protein amino acid sequence, where each sequence is made up of individual amino acids. So we see here that there's this label encoding part and this embedding layer part. And that's actually what we're just going to go over right now. And the reason we need to have these two layers is because our input data are in the form of strings. We need to convert them to numbers. And that's what these two layers are doing. And then we have these multiple convolutional layers. Another thing to say is, although we're building a convolutional neural network, another difference between this and convolutional neural networks for image analysis is that we'll be using one-dimensional convolutions, not two-dimensional. And I'll describe that better in a few minutes. So we have these two towers of neural networks that produce representations learned representations of SMILES input, drug input, and protein sequence input. And then, and this is a common feature of many deep learning approaches, when you are deriving information from different sources, it's not uncommon to then just concatenate the derived information. So we have these two learned representations, and then we just put them side by side. So we concatenate them. If you're familiar with recurrent neural networks or LSTMs, within an RNN cell or an LSTM cell, you see this kind of concatenation. And so that simple concatenation produces a combined representation. And that combined representation in turn forms the input for a third neural network. So this whole thing is one neural network, but you can think of it as being divided into three smaller neural networks. And that third neural network that sits on top of these two towers is just a multi-layer perceptron. And there have been many previous VLEs on multi-layer perceptrons. And finally, we're making this one neuron output prediction, Y, which in our case is the PKD. So it's basically just a regression task. So that's their model there. And as you'll see, we will try to recapitulate this model as faithfully as possible. Okay, so I mentioned this label. So the first step is this label encoding part. So highlighted here, they show you what this means. And it's, they give you an example input string, and then they show you the corresponding, what they're doing is they're assigning an index to each input. So for example, C is 1, H is 2, N is 3. So this kind of string would become just a series of numbers. And we do the same thing for the amino acid sequences. And so this process is called tokenizing. And you could do for natural language processing where you have individual words, you would assign a unique index to each word. In this case, everything is happening at the character level. So to tokenize at the character level, we can use this tokenizer. And we just have to specify that the character level is true. And we do this separately for the SMILE string and the amino acid strings. So the first step is to just set this up, just to create this tokenizer object called tokenizer_smiles. And then we fit this object using our trained SMILES data. So this is an important thing, just generally in machine learning. Anytime you do this, all this fitting happens only using your training data and never your test data. So we use a special fit on text. And then, so all this is doing is it is assigning, it's working out all the unique characters that are in our collection of SMILE strings and assigning a unique index to each unique character. So that's the step here. And then if you wanted to get the word index, so the word index is just a dictionary that shows you what index corresponds to what character. I see that there's a question. The question is, to what extent does this account for multiple binding sites and side effects? I'm not so sure about side effects, but multiple binding sites. It might indirectly account for that, but I don't have a ready answer. As you'll see, when we do the build a convolutional neural network, what we're basically doing is we're generating multiple filters that are looking for, separately, they're looking for motifs in the protein sequences, and they're also looking, I guess they're also looking for motifs in the SMILE strings. So they might indirectly that process might indirectly identify key binding sites. And if there are multiple binding sites that contribute to the score, then that will be picked up. sorry, that was not, I don't think that was a great answer, but okay. All right, so we have, I mentioned this word index, and the word index is just a dictionary that translates, that shows you what index corresponds to what character. And at this point, I just wanted to work out the length, so how many unique characters there are. And the reason I do this is this vocab underscore size underscore smiles is something that I will be using later on. Because right now, these, each character has a unique index, like 1, 2, 3. This, so that's this label encoding. What I then need to do is I need to pass this through an embedding layer. And the embedding layer, that takes in, does not take in indices, that takes in one-hot encoded versions of each index. And so if you're not familiar with one-hot encoding, you can think of it in this way. Imagine instead of all of this, you had a simple data set of the entries were cat, dog, and cow. Their corresponding indices could be 1, 2, 3. The one-hot encoded versions of that would be 100, 010, and 001. And that's it. And so once we worked out this word index, we can then pass all of our smiles data, so all of our drug strings, through this text to sequences to convert all the smile strings into these sequences of numbers. And so we get this train underscore sequences underscore smiles. And that's great. So now at this point, so this highlighted line here, every drug in our data set has been converted into a sequence of numbers. Now, because different drugs, as you saw in the distribution that they had worked out, not every drug has the same length, which makes sense. This is problematic. So we need to ensure for our neural network, which is expecting a fixed length input, we need to provide it that. So to do that, we can do this thing called padding. So we can use this pad underscore sequences. And I should say, I'm going to scroll back up. All of the importing was done here. So pad underscore sequences is imported from this module, tokenizer is imported from this module, and so on. Okay, so we have pad underscore sequences, and we have we have 3 parameters here. There's multiple parameters, but we're just going to use 3. So the padding we're doing is post. So all padding means is we need to specify a fixed length. And so we specify that using this max length. So that equals 85. So that ensures that every drug input is going to be exactly 85 characters long, or actually numbers long. And the reason I chose 85 is because that's what that's the number that the authors of the DeepDTA paper recommended. And so what the padding does is it just, so in this case, padding is, I decided to do post-padding. I'm quite sure that pre-padding would work, would also work well. It just, so if a given input drug has fewer than 85 characters, this would just add a bunch of zeros to the end so that it was 85 characters long. Now, if the input drug were longer than 85 characters, we have to deal with that in some way. So we have to truncate it. So again, I chose to truncate it at the end. Again, these are things that beforehand, it's hard to predict what the effect will be on the outcome. So you could try truncating pre and padding pre. You can also try different lengths. So that's all of that. And so that's how we've now tokenized our train smiles data, and we can similarly tokenize our test smiles data. And to do that, remember, we've already fit on our training data. So we just have to pick up from the text to sequences. And again, we pad those sequences. So if I run this, yep, so it did that pretty quickly. And then we do the exact same thing for the proteins data. The only difference here is the max length we choose, because the proteins are typically much longer than drugs, we pick a different size. So in this case, it's 1200 instead of 85. So this will take a little bit longer to run just because the sequences are much longer. Great. And then I just wanted to get a sense of how long these one-hot encoded representations of each character would be. So you can just print, this is the size, the one-hot encoded size for the smiles and the proteins. And these are two numbers that we will use later on in our neural network. So just a small detail about these two things that we've just created, the test padded proteins and the padded proteins and padded smiles for training and test, is that those are all lists. And we need to convert these lists into arrays. And that's just because that's the data type that our neural network is expecting. So to convert them into arrays, it's really simple. We just do np.array. So using the Numpy package. One thing I did specify, so these first 4 arrays that we generate, those are all of the data type for all of these arrays is the int data type, integer, which is fine. However, for the labels data, so these are the PKD values, these are floats. Now, the default data type for a NumPy array is float 64. So here I'm just specifying float 32, because again, typically the neural networks you make in TensorFlow and in Keras are expecting this specific data type, 32, not 64. So that's it. That's why just for these two, I explicitly specify the data type I want. And then I print the dimensions of each resulting array. So I use this shape method. If you're unfamiliar with NumPy, this is probably the most important package to learn and get used to. So we can see that for the first few arrays, first 4 arrays, we have 2-dimensional objects. So in this case here, the train smiles array, we have an array that has 21,406 rows and then 85 columns. And so this shows you that both the drug data and the proteins data, all the inputs have the same sequence length. And then finally, we have train labels and test labels. And you can see that the numbers correspond as they should. Okay, so as you can see, there's not a huge amount to do to get our data into the form we need them in. Okay, so I have imported a few more layers, well, the layers that we need to build our neural network. One thing I should say here is Keras offers multiple ways of building a neural network. If you watched my previous VLE, I used what's known as the sequential API. And that's in many ways the simplest way to build a neural network in Keras. And it's, I say it's simple because we think of a neural network as a sequence of layers, and the sequential API, it allows you to build a neural network that is simply just a sequence of layers. There are 2 other ways of building neural networks. One is the subclassing API, which uses this object-oriented programming approach. And that's something you will be familiar with if you prefer PyTorch. And the third way is this functional API approach, which is the approach we'll be using. The functional API approach and the subclassing API, they are particularly useful when you're trying to build slightly more complex neural networks like this, where you have this kind of 2 neural networks that are working in parallel, and then they combine to form a third neural network, that kind of thing. So the reason this is called a functional API is because we can, in this case, think of our various layers as functions, meaning that they take in an input, They do something to that input and they produce an output. And so, for example, I'm skipping to this line here. Oops. This embedding layer. We have embedding, and then we specify some of these parameter values. And then we can see that after we've done that, we just, again, in parentheses, put in an input, some kind of input. And that input in this case is the smiles input. And that produces an output. And the output of this line becomes the input to the next line, and so on. And this is kind of written in the form, if you're familiar with functions in any language, this is kind of similar to the syntax you would use. Okay, so we first need to specify our input layers. And the reason we need these input layers is we need a way of telling Keras what the input dimensions of our data, input data, are going to be. So in the case of the smiles input, I mentioned that it's a vector that is 85 numbers long. And for proteins, it's another vector, but in this case, it's 1200 numbers long. So we have these two input layers. And I will build the two towers, the smiles tower and the proteins tower, one after the other. So I've called the smiles tower the smiles encoder. And so we have an embedding layer. And to build an embedding layer, we just use the this embedding layer. And it takes in a few inputs. One is, I mentioned this one hot encoded representation of each input. So that's this here. So it's the length of the vocabulary for the smiles data, which we worked out previously, +1. And the +1 is, I believe it's to account for, it's kind of like a wildcard in case it sees something that in the test set that it didn't see in the training set, or maybe in another data set that you use. So it has that one extra number to account for that. So that's kind of, that's one entry, the one thing that you need for the embedding layer. The second thing is this 128, and 128 refers to the dimension of, or the size of the embedding that I want Keras to learn. So this one hot encoded representation is just a way of assigning a unique value to each input. So each amino acid or each atom. The problem with this is it doesn't give you any information other than the index. So what we want to do is we want to convert this one hot encoded representation into another representation or an embedding that can be tuned and will hopefully capture some kind of biologically relevant information. And so that's what this embedding layer is doing. That's the purpose of this embedding layer. Why did I choose 128? Again, that's the number that the authors of this paper chose. And this is another hyperparameter that is worth testing. So if it's too small, then your model won't be expressive enough, and your embeddings won't be big enough to fully capture the biological nuances. Conversely, if they are too big, then you have an over-parameterized model, and you can run into the risk of overfitting. So 128, again, I believe that's what the authors chose, so I chose 128. And then we need to specify the input length, which is a fixed length. So in this case, it's 85. And as I mentioned, since this is the functional API, this is the syntax you use. So that is, so this line here, the first line of the smiles encoder, corresponds to this embedding layer here. So we've done the encoding, and now we've moved on to the embedding layer. The output of the embedding layer will be the input to our convolutional layers. So that's here. Embed smiles is the input to the first convolutional layer. And as I mentioned, one difference between this kind of convolutional layer and the ones you use for image analysis is this is conv 1D. If you were doing image analysis, you would be doing conv 2D. And so what does this 1D mean? When I first came across this, for whatever reason, was a little bit confused about these dimensions. because, oh, I should say, once you've learned these embeddings, so one thing that's maybe a little bit tricky to keep track of is how the dimensions of your data change as they are passed through the network. So once your input data are passed through this embedding layer, what you get is for each drug, there's a question. How can I get the recording of this presentation? Tiffany will send you a link later on. All right, so we have the embed smiles. So the dimensions of this will be 85. So 85 refers to the fixed sequence length by 128. And that's because each of these 85 atoms and bonds in this case have a corresponding embedding that is 128 numbers long. So we go from this for each, so each entry is just a vector, a one-dimensional vector that is 85 numbers long. When we pass it through this embedding layer, it becomes a two-dimensional matrix that is 85 by 128. And if you're familiar with image analysis, images are also, like for example, a black and white image is a two-dimensional object consisting of various numbers, where each number is a pixel value. In the case of an image, when you do a convolution using a filter, you move first across, so across the x-axis, and then you move down, and then you move across again, and down, and across again. So you're moving your filter, your convolutional filter, both in the x-axis direction and the y-axis direction. In the case of one-dimensional convolutions, as you would use for text data, you are taking your filter that in this specific case will be 4 by 128. And then you move that across your sequence. And you are only moving from left to right. There's no downward motion. So you're only moving across the x-axis. And because you're only moving in one dimension, it's conv 1D. I apologize. I should have maybe made some illustrations to help better describe what I'm trying to describe, but hopefully, hopefully you understand what's going on here. All right, so so for the conv 1D layer, we need to specify a few things. One is the number of filters that we want to use. So again, I've said this many times, I'll say it again. Why did I choose 32? Because the authors chose 32. So that refers to the number of convolutional filters we'll be using for the first layer. The second number, this number 4, refers to, as I mentioned, the one dimension of this filter. So the other dimension is fixed. That's always 128. But the 4 refers to, in this case, maybe 4 atoms or a combination of atoms and bonds, just 4 long. And all the other parameters I've left as defaults. And the only other thing I've specified is the nonlinear activation, because when it comes to neural networks, you need two things. You need layers and you need nonlinearity. And the nonlinear activation function that I'm using is ReLU, the rectified linear unit. And this is a general purpose activation function that works really well. There are others, like CellU, LU, and so on. ReLU seems to work nicely. And it's also the function, they don't say it here, but it's also the function that the authors used. So that's the first convolutional layer. And then what we do is we take the output of the first layer and we use that as input for the second layer. So that's this one here. And the difference between, and in this second layer, what we have is we've doubled the number of filters. We've increased one dimension of the filters. And we pass that, the output of that, to the third layer. And in that case, again, we've increased both the number of filters and the dimensions of the filters. And finally, so the output of all of this is will be two-dimensional for each individual entry. And what we want is for this concatenation step, So these representations, we want these representations to be one-dimensional vectors. So one easy way to do that is to use this global max pooling 1D. So it just works out at each index, it works out the maximum value. And to produce this max smiles, and max smiles is just a vector. And I have this line commented. I'm actually just going to delete it. It's something that I was trying out later on, but I forgot to delete it. Okay, so that's the smiles encoder part to get your smiles representation. So that's all the way up to this smiles representation. And then we do the same thing for the proteins encoder. We just change, we just change, a couple of numbers, but otherwise everything else is the same. We get this max protein, which corresponds to this sequence representation. And then we concatenate them. And to concatenate, we use a concatenate layer. And that looks like this. So we now have this concat layer, which is the combined representation. And then we use that as input for this final neural network that is sitting on top. And I've decided to call that the decoder. And again, all of these numbers that I've specified. So fully connected layers in Keras are called dense layers. So we use these dense layers. And these number of neurons that I've specified were, again, numbers that the authors used. Similarly, we always seem to be using the ReLU activation function. One new thing is this dropout layer. And if you're unfamiliar with dropout, it's a really simple concept. It's a way of preventing overfitting of your model. And having dropout layers during the training process randomly drops out a given percentage of neurons. So in this case, 10% of neurons for these layers. And the reason you would do that is you don't want to develop you don't want your model to develop an over-reliance on specific neurons. So this is one way to avoid that. But as you can see, putting in a dropout layer is really straightforward. And then we have a final dense layer where we just have one output and no nonlinear activation. And this is the PKD output that we're trying to predict. So since we have these two encoder components and this decoder component, we now want to put them all together to form one unified model. And to do that, we can use this model equals capital M model, and we specify the inputs as a list. So, and yes, and then we specify our output. Right. So I'm going to run all of that. And I've just repeated myself here, but it's okay. So now once we've built our model, what we want to do is we want to compile the model. And so what we mean by that is when we compile the model, we need, it gives us the opportunity to specify various things. Like we can specify the loss function. And this is important because this is how learning happens. Then the objective is to modify the parameters of our model so as to minimize this loss. So in this case, the loss we specify is MSE, mean squared error. It seems to be a reasonable loss for this regression task. We can there are others that are available like mean absolute error, Huber loss, but MSE is a pretty standard one. And then we need to specify some kind of optimizer. So the simplest one we could specify is stochastic gradient descent. We'll be using this thing called Adam, and Adam, you can think of it as a superior version of stochastic gradient descent. And then we can optionally specify metrics, and this is for our benefit. In this case, the metrics and the loss are the same. So this is actually not super useful, but if you were doing a classification task and your loss function were, for example, were cross entropy and your metrics were accuracy, then it would make more sense. In this case, it's a little redundant, but I'm just going to leave it there so as to not break the code later on. And this, I want to show you a couple of things that really makes Keras shine. One is, so We just run, so the model that we built, that we just called model, it has a method called summary, and it shows you each of the layers that you have generated. And just as importantly, it also shows you the dimensions. I mentioned, like, as your input is passing through your neural network, the dimensions will likely change. Sometimes it's difficult to keep track of that in your head. So this tells us exactly what is happening at each layer. And also it gives you the number of parameters in each layer. And one thing I should say is this none here, that just represents the batch size, because it doesn't, you have so far not specified what batch size you're going to use. So it just puts in this none to represent something that is variable. And finally, it also tells you the number of parameters, and that's, I guess by modern deep learning standards, this isn't big at all, but it's still pretty big. So it's almost 2 million parameters that this model contains. So this is one useful way of seeing what you've made. Another way is to use this plot model function. And this is really nice because it kind of reproduces this nicer figure in a simpler form. So you can see these two towers. You have the learned representations, you concatenate them, and then you have the third neural network and a prediction. Okay. I mentioned the danger of overfitting, which is ever present in machine learning. One way to handle that is to use this thing called early stopping. And the problem is, if you keep training your network, what can happen is that your network's performance continues to improve on your training set, but worsens on your validation or your test set. So one way is to set up this early stopping. This is known as a callback. So to set up this early stopping callback, so it monitors your validation loss. Actually, it can monitor various things, but by default, it monitors your validation loss. And the minute it sees that there's no longer any improvement, and you define what that means, it will stop training. And it has this nice feature here, this restore best weights. So it won't just keep the weights of the most recent epoch. It will look back through its history and restore the best weights. See, there's a question. Can you explain more the difference between the learned and original representations, and why do you need a learned representation? That's a good question. So you are asking about the difference between this embedding layer here and the smiles representation here. That is a really good question. So one answer to that is, if you were to just put in your one-hot encodings into your convolutional layer, that would be dependent on the specific one-hot encoding you used for your inputs. And since I mentioned that the one-hot encodings beyond just giving you the index of a particular character don't tell you anything, your convolutional, your CNN blocks won't be learning anything meaningful. So the input to these two neural networks has to be something meaningful. And if this were image data, it's already in a meaningful form. You don't have to embed it in any way. But text data doesn't come in a meaningful form, so we have to learn it in some way. One way to get around this in, for example, actual text data, is that these embedding layers are learned, or these embeddings are learned separately, and then they're used as input. That's a really good question. The point is, we need to have some meaningful embedding here for this to work. And then these representations represent what the network has learned. Although So the reason we do this is because we don't have embeddings. But I do wonder if we go through this entire process, if afterwards these embeddings, now that we have these embeddings, we can just skip the CNN blocks and then use these, concatenate these two and pass them through a network. I suspect the answer is yes. So in that case, if let's say somehow magically you had a dictionary of meaningful embeddings for your smiles and your protein. But even in that case, these smiles representations and these encodings are specific to the task at hand because you're predicting the combination of the two. But yeah, I'm going to say it one last time. If you just had one hot encoded inputs into your CNN blocks, you wouldn't learn anything. But thank you. That was a great question. Okay, so we have early stopping, and actually we have another 10 minutes. I think we have enough time to train this. So the final thing to do is to just fit the model or train it. And you can see here, we have two. So typically when you train it, you have one input and you have one set of inputs and one set of labels. Here in this case, you have two sets of inputs. You have your smiles inputs and your proteins inputs. And so you put them in together as a list. Actually, I'm just going to go ahead and start training this, and I can describe this as this is training. And then you have your labels array. And then the epochs refers to, so one epoch refers to when all your training data have passed through your network. So we won't be passing them all at once. So typically for large data sets, we pass in randomly selected batches of our data. So one epoch represents all the batches being passed through, and we do this 100 times. And the early stopping, so 100 might seem like a lot, but the early stopping is what stops our model from overtraining. And then the batch size equals 256. Once again, I believe I chose this based on the recommendation in the paper. And then you can also put in your validation data here. So that's our test smiles array. So again, in the same format, we have a test smiles, test proteins as inputs, and then we have our test labels as what we're trying to predict. And you can see Keras has this nice formatted way of showing you the loss. So in this case, like I said, it's redundant. The loss and the mean squared error are identical. So these values are also identical. But you can see the loss for your training loss after each epoch and your validation loss. And you should hopefully see both of them decrease. And you can see, so the validation loss is a better indicator of how well your model is learning. So we start off at this 0.54 value, and you can see it kind of jumping up and down, but I have previously noticed that it starts off with modest improvements, and then it starts to go down faster, which is interesting. Or that might not actually be true, but it does decrease. One thing worth mentioning here, so early stopping, I specified these two parameters. So this min delta just basically means, as I said here, the minimum amount of change to count as an improvement. So if it improves by less than this, then that's when early stopping kicks in. Now, one thing is you saw here that sometimes the validation loss can spike, like can go from 0.44 to 0.47. That is not necessarily an indication that things are becoming worse. It's just because of the stochastic nature of how you choose how these batches get chosen. So you want to kind of give your model some room to allow for these random spikes. And so you can do that by specifying this patience parameter. And that basically says that if I don't see any improvement, specified improvement for 10 whole epochs, then I will stop. But if you want to take a more conservative approach, you can set the patience to less than 10. And so it's continuing to train. You can see from now gone down to now it's like 0.2 something. And I believe it should, the early stopping should kick in. So don't worry, it won't go all the way to 100. But while it's training, does anyone have any other questions? Or for the people who've asked questions, would you like me to try to improve my answers? All right. Hopefully this is nearly done. All right, it's taking a little bit longer than I thought. So I've done this here. I like to see how the training proceeds. So I usually just leave this on. If you wanted to switch this off, you can just set this model.fit has an additional parameter called verbose. You can just set verbose equals to 0. And then you will just see your cell running, but you won't see this output. Gosh, this is continuing to go on. It's a bit of a shame because I can't stop this to see the rest. What I'll do is I'll start to describe. Okay, so from when I did this, to let this run. When I did this previously, I still have the output from when I did this previously. So just using the using PyPlot, you can plot the your mean squared error at the end of each epoch for your loss and validation. And to do that, so I didn't mention here. Sorry. You can just run model.fit as is, or you can save the output of model.fit by assigning it to this object called history. And that's history is an example of another callback. And from this history object, by typing this history.history, you can get the mean squared error for the training mean squared error and the validation mean squared error. And so then you just plot the mean squared error against the number of epochs. And you can see that both the training and validation error, for whatever reason, the training error starts much higher. Likely because of the batch size. You can see both of them decrease until a point where the validation error is no longer decreasing meaningfully. Which is good. So it shows you that it's learning something meaningful. Yep, done. And you can see it stopped at a mean squared error of 0.2, which I believe is lower than in the paper. But in the paper, they do cross-validation. So that probably explains why they got a higher mean squared error. And then if you want to save the model, it's just model.save, and you save it as this H5 object. And to load it, it's just literally, you just load model. And then just to make some predictions, I wrote this simple function here that takes in inputs and produces a PKD. I won't go to the details, but it's basically just recapitulating what we did previously to convert your input into a form that your neural network can recognize. And then I just picked this from the test set. I picked a few entries just to see what they looked like. I picked this one, 1531, because it's the longest entry. So I was curious to see what the output was. And you can see here that the label is 10.4, the PKD, and the prediction is almost 8. And since this is on the log scale, there's actually quite a big difference. But just to show you that this is learning at least something better than just pure chance, if you just change it to something else, you see a precipitous drop in the prediction, or a much bigger difference between the prediction and the real value. And you're welcome to try out different combinations just to convince yourself that your model's prediction is as close to the real answer as any other, compared to all the other predictions. Yeah, and then this is the code you need to run to load your model. And if you're interested in both pursuing this sort of approach, but also learning about the various ways in which deep learning has been used and is being used for in biology, I strongly recommend reading this review. It's really great because it shows you how to perform these kinds of tasks, but it also shows you how you can use generative neural networks to do much more sophisticated things like design new drugs and proteins and things like that. Finally, I want to say that this approach is actually quite simple because we're taking one-dimensional data, but obviously drugs and proteins aren't one-dimensional objects. So recently, there's been a lot of research on neural networks that take advantage of this spatial information. So like graph neural networks and the various varieties of graph neural networks. And the implementation of those networks is pretty straightforward in both Keras and TensorFlow. And if you prefer PyTorch, there's PyTorch Geometrics that was specifically designed for that. All right, it's exactly 5. So thank you so much for your attention. As I mentioned, I will ask Tiffany if she can share both the code and the data set so you can go through this on your own. And if you have any questions, even afterwards, please feel free to email me. Just give it a few more seconds to see if there are any lingering questions. Don't see any. All right. In that case, thank you for your attention.